Hello everyone, my name is Calarina Muslimani and I'm from the University of Alberta. Today I'm going to be presenting my work titled Comparing Feedback Distributions in Limited Teacher-Student Settings. This work was done in collaboration with my two awesome co-authors, Kerrick, Johnstonbaugh, and Dr. Matthew E. Taylor. I'm going to begin by providing an overview of the teacher-student framework. In this framework, there's a teacher agent that provides guidance to a student agent during the student's learning process. The teacher can be either human or another artificial agent. In addition, guidance can take on several forms, such as learning from demonstration, as well as action advice or evaluative feedback. In this particular work, we focus on a student learning from evaluative feedback, where a teacher provides feedback, for example, good or bad, to a student agent based on its actions. We chose to use evaluative feedback because it operates at a higher level of resolution compared to other mechanisms like action advice. Furthermore, evaluative feedback can be applied across sequences of actions. It is not limited to an action-by-action basis. In addition, the number of feedback choices can be much smaller than the number of actions in an action space. Having fewer options to choose from can make it easier for a human teacher to guide a student. However, what problems arise in the teacher-student framework? A prominent issue involves communication constraints. For human teachers, fatigue and attention span can hinder their ability to teach students over an extended period of time. For both human and artificial teachers, there can also be a cost to teaching. More specifically, one option to obtain human teachers in such studies is to use mechanical Turks, which can be expensive. Lastly, teachers may want to teach several students at a time. In this manner, a teacher must divide its time amongst several students. One commonality amongst these constraints is the need to limit the amount of interaction a single teacher has with a student. Therefore, a possible solution to this overarching problem is to make use of a feedback budget. In our setting, we use a feedback budget to limit the number of times a teacher can provide feedback to a student, therefore reducing the total number of interactions between student and teacher. Now, with this in mind, the overall goal of this work is to investigate this question. Given a limited feedback budget, when should teachers provide feedback to students in order to maximize student performance? In other words, how can a teacher best leverage the limited number of interactions it has with the student to enhance student learning? In the teacher-student framework, understanding which teaching strategies teachers should employ is vital. By finding optimal feedback strategies, we can not only better teach other agents, but possibly use such strategies to improve how humans teach other agents. Now, in order to understand when teachers should provide feedback to students, we begin by discussing possible feedback strategies. We adopted 3 teaching heuristics originally used in the action advising setting. I'll use the following clipboard as a running example to describe all strategies. First is early advising, where the teacher provides feedback during the first X number of time steps. Suppose our teacher had a budget of 8 feedbacks. Let the green blocks denote the first 8 states the student encountered on its path. Then the teacher will provide feedback for the actions the student took at each of those states. Feedback here is denoted by the yellow stars. Next, we move on to the alternate advising strategy, where a teacher provides feedback every U time steps. In this example, suppose U was 4, so the student would receive feedback at every 4th time step as shown in the figure. Lastly, we have importance advising. In this strategy, the teacher provides feedback at states where the difference between action values is large. For the clipboard environment, we know that there's a large negative environmental reward for actions that leads the agent off the cliff. Therefore, states surrounding the cliff would be considered important according to this metric. In addition, we developed a novel teaching strategy we call Visitation Advising. This is based on the intuition that states the teacher visits more often should be learned by the student. The SARSA algorithm is readily known to take this path in the cliff world as shown. Therefore, if we had a SARSA teacher, then the student would receive feedback only along these states. Now we move along to our experimental setup. Our work is motivated by the potential of a human teacher. However, we decided to use an artificial teacher to create a more controlled initial setting. We use a reinforcement learning algorithm to train the teacher agent. In addition, the main 2 criteria for the teacher agent is that the algorithm it was trained with is value-based to enable importance advising in that it has the optimal policy for the task. This is followed by the student agent, which learns by a supervised learning algorithm called Tamer, which I will discuss in more detail on the next slide. Lastly, we ran our comparative analysis on 3 increasingly complex domains: Lava World, which is a tabular grid world, followed by Mountain Car and Lunar Lander. Due to limited time, I will focus the empirical results on the Mountain Car task. Now I will give a brief overview of the Tamer algorithm. With this supervised learning algorithm, the teacher agent aims to approximate the teacher's reinforcement function labeled capital H. Its goal is to maximize immediate teacher feedback because the teacher's reinforcement is a direct label on recent state action pairs. Furthermore, to better understand Tamer compared to typical reinforcement learning algorithms, I will review the diagram on the right. We see that the student interacts with the environment in a similar MDP fashion. The main difference is the environment does not provide any reward to the student agent. The teacher will watch the student as it traverses the environment by receiving its states and actions, and will provide feedback to the student accordingly. The student will only learn from the feedback the teacher provides. Now I'll discuss our findings for the Mountain Car domain. We used a source teacher that had a budget of 75 feedbacks. Student performance in this task is defined by the average number of time steps to reach the goal. On the graph to the left, the blocks indicate the training episode in which the budget was complete for each of the 4 training strategies. We found that the use of different feedback strategies did affect student performance. More specifically, we found that the student achieved its best performance when being taught with alternating advising, which is denoted by the blue curve. However, it was unable to reach the optimal policy, which is denoted by the black dotted line. We infer that the low budget was a factor impacting the student's ability to reach the optimal policy. Now, what areas of the state space did the student actually learn? Here we have a heat map, which shows how often feedback was provided to the student at different regions of the state space. Darker color indicates more feedback was provided at that region. We compare the feedback distribution for visitation advising, which is shown on the left, and alternating advising shown on the right. We see that under visitation advising, the teacher provided most of its feedback around the start state of Mountain Car, because the start state region in Mountain Car is when the position of the car is between -0.4 and -0.6. And we see from the heat map, this region is the darkest in color. But why did this occur? In Mountain Car, the teacher's policy has to gain momentum and move back and forth through the start state region in order to reach the goal state. This explains why the student received most of his feedback in this area. We found there was alternating advising. The teacher provided its feedback in a more uniform manner, which allowed the student to learn more of the state space. We infer that this enabled the student to learn a better policy. So who's the winner? Overall, we found that there was no clear winning feedback strategy across all 3 environmental domains. We infer that the efficacy of the strategies can be environment dependent. However, we did find that the distribution of feedback does impact student learning in terms of both learning efficiency and the quality of the policy learned. So what comes next? There are several areas that need to be explored given our current work. We found that Tamer's inability to propagate feedback to past states and actions was a limiting factor. More work needs to be done to explore whether other teacher-student algorithms can be used that take into account past state transitions. In addition, our visitation advising strategy was constrained by its inability to directly associate visit counts with states in non-linear function approximation settings. Further studies can explore how to define visitation metrics in such settings. Overall, understanding optimal teaching strategies needs to be emphasized within the RL community, and more work needs to be done to explore how and when teachers should teach other agents. I hope you enjoyed listening to my presentation, and thank you for your time.